Welcome. In this session, we'll look at this Heaviside step function and the design matrix that we'll need for artificial neural networks. Our problem is supervised binary classification. And what that means is that we are given M data, and these are usually given to us as vectors that will denote X, and we'll subscript them J, and each one of them has N entries. And because this is supervised binary, that means we have M labels, and these are values that we'll denote as Y, and each one of those values is either 0 or 1. And the idea behind supervised binary classification is we would like to predict each of these X vectors to be in its corresponding label. So what we want to do is we'll explore a linear problem first, which is what we want to do is find a weight vector, and in the interim we'll denote this as W with a hat on it, and this has N entries, and we also need a bias scalar, and we'll denote that as a value B, and that is a real number. And what we'll do is we'll predict, and I'll just say based on, that is we'll have to do something else with this, but we'll be based on the idea that we'll have a scalar U, and we'll compute that as the transpose of the data vector times this interim weight vector plus the bias scalar. And what we want to do is we want to map this U onto the set 0, 1. So that's what we would like to do. And the way this is most commonly done is with the Heaviside step function. So this is named after the great mathematician, engineer, and physicist Oliver Heaviside, and it's sometimes called a step function. And it is a straightforward definition, is that the Heaviside function of some value V is 0 if the value V is negative, and it is 1 if the value V is not negative. And we could draw that, we could graph that, we could imagine this is our V, and this is the Heaviside computation, is if it's less than 0, it will be 0, and then it will jump to 1. And in calculus, we might put a little circle here to indicate that that's an open set, and we might put a dot here to indicate that's a closed set. We'll just leave this for now. And one example use is we might want to take this and quantize it. So we might define a function Q, which takes our data vector, our interim weight vector, and our bias scalar, and we could compute that as the Heaviside function of the dot product between the data and the interim weight vector plus the bias scalar. And that would accomplish this mapping. The way that we'll do it is we'll gather all of these data into a design matrix. So what we'll do is we'll observe that U, which is X transpose W hat plus B, that another way that we could represent that is we could say, let's take the X vector and let's transpose it, and then we'll append a 1 to it, and then let's take the interim weight vector, and let's append to that the bias scalar. And if we did that, what we would see is that this scalar can be written as in another way. We could say that that is a 1 form times an augmented weight vector. And this idea of augmenting is quite common in neural networks where we have these bias terms. And from prerequisite courses, we can recognize that what this computation is doing is it's drawing a hyperplane that has a not necessarily unit normal of W hat and a bias B, and U will be negative if the data vector is on the negative side of the hyperplane, and it will be positive if it's on the positive side of the hyperplane, and U will be exactly 0 if the data lies on that hyperplane. What we can now do is we can now gather the data. And what we can do is we will use a capital X for our design matrix, and we'll define that for the purposes of neural networks as being X1 form 1, X1 form 2, and so on to X1 form M. So this will be an M by N plus 1 matrix. And another way that we could write that is we could say that that is X vector 1 transpose followed by a 1, X vector 2 transpose followed by a 1, and continue until we get to X vector M transposed followed by a 1. And these would be the same way of writing, different ways of writing the same thing. So we will write row number J of X as, we'll write that as the jth one form X. And now we will predict based on uj, which we'll say is X1 form j times the augmented weight vector W.